Hello everyone, this is Tejas Raj from Sri Venkateswara College of Engineering from the course of Data Science, and I am here to discuss about the mathematics, the discrete mathematics. The topic is about recurrence relation. So a recurrence relation defines a sequence where each term depends on previous terms. For example, we'll take about a Fibonacci sequence, so everyone knows about it, where it comes under DSA. So in this, for example, if we take in Fibonacci sequence where 1, 2, 3 and up to n in a given form of set, if 0 plus 1 is equal to 1 and 1 plus 1 is equal to 2 and 1 plus 2 plus 1 will be 3. So in that way, the Fibonacci sequence is created in a given set. So in this, used in algorithm, financial modeling and discrete mathematics. So these are the examples for or introduction for recurrence relation. So let's move on. So as I discussed before, so what is recurrence relation? A recurrence relation is an equation that defines a sequence where each term is defined as a function of processing terms. Then for example, the Fibonacci sequence where f of n is equal to f of n plus 1 plus f of n minus 2 is a classic example for recurrence relation. So the next is applications. Where are the applications are used? There are crucial in algorithms, divide and conquer, where we see in DSA, financial modeling and discrete mathematics. So we'll see what is given. Before we dive into the specific of homogeneous recurrence, let's briefly review what is going on. So it's a way to define a sequence where each term is expressed in terms of one or more of its previous terms, as we know that. So let's now defining homogeneous. So key characteristics. A recurrence relation is homogeneous if the equation if the equation equals 0 when all terms involving the sequence are moved to one side. This means there is no extra term that are not part of the sequence or its shifted version. The general form is a of n is equal to c1 a of n minus 1 plus c2 n minus 2 plus up to ck a of n minus k, where c1 is a constant. A homogeneous recurrence relation is a specific type of recurrence relation where each term is defined as a linear combination of previous. There is no additional non-current terms. This means that if you move all the terms involving the sequence to one side of the equation, the other side of will be 0. So this is the recurrence topic. So let's move. Now we'll discuss what is constant coefficients. So what are they? Constant coefficients refer to the numerical value like c1 and c2 etc. that multiply the previous terms in the recurrence relation. This coefficient do not change with n. Then significance. The constancy of these coefficients allow us to use a powerful technique involving characteristics equation to find explicit formulas for the sequence terms. Contrast. In contrast, recurrence relation with variable coefficients, for example a of n is equal to n into a of n minus 1, are much harder to solve and often require different methods. Then the constant coefficients, part of the name is crucial. It means that the multipliers of the previous terms in the recurrence relation are fixed numbers, not dependent on the index n. This property is what enables us to use the characteristics equation method, a cornerstone for solving these types of problems without constant coefficients. So now we'll see about what is the characteristics equations. In this, what we'll do means replace a of n with r of n and derive a polynomial. Solve the polynomial to get the roots. These roots determine the root form of the general solution. Now we'll see about the second order homogeneous recurrence. So in this, where a of n depends on a of n minus 1 and a of n minus 2. The all types of root obtained by the characteristics equation determines the form of the general solution. We primarily encounter these cases: distinct real roots, repeated real roots, and complex recurrence relation. Initially, conditions are then used to find the specific constants. So as you can see in this, distinct real roots, if r1 is not equal to r2 are real roots, the general solution is a of n is equal to a of r1 upon n plus b r2 upon n. So in the complex conjugates roots, if r is equal to alpha plus or minus, I is nothing but it is an root of minus 1. So it is a complex number. I beta. Convert to polar form r of cos theta plus or minus, again iota sine of theta, and use a of n is equal to r of n into a into cos of n theta plus b into sine of n theta, where n theta defines the overall of the loop. Here is a step-by-step solution for solving the recurrence relation. The first thing is like find the relation. Given a of n is equal to 5 of a n minus 1 minus of 6 a n minus 2 with a naught is equal to 2 and a1 is equal to 5. So this is an example which I have taken. Then the second thing is form characteristics equations. To form that, you need to solve the particular solution. For example, r square minus 5r plus 6 is equal to 0, as the a1 is equal to 5 and a0 is equal to 2. Then we need to find the roots. By using the formula we can also find the roots, or by the polynomial method. So in this factorizing, r minus 2 into r minus 3 is equal to 0. So r1 is equal to 2 and r3 is equal to 3. So in general solution, a of n is equal to a of 2 power of n plus b of 3 power n. Then we need to apply initial conditions using a0 is equal to 2 and a1 is equal to 5. We solve for a and b, and then a plus b is equal to 2 and 2a plus 3b is equal to 5. This yields a is equal to 1 and b is equal to 1. So these are the real roots which we find out. The final solution will be a of n is equal to 2 of n plus 3n. So this is the final solution we get by solving the given problem. So let's walk through the concrete example to solidify our understanding. So in this, a0 is equal to 2 and a1 is equal to 5. By following the steps of forming the characteristics equation, finding its roots, constructing a general solution, applying the initial condition, we can derive an explicit formula for an a of n. So this systematic approach ensures an accurate solution also. So let's move on. Dealing with repeated roots also is possible. It tells that equation when the characteristics equation has a repeated roots. Let's say r of multiply m. So it will be like r of multiply m. Then we'll see a form of solution. The corresponding part of the general solution will be c0 plus c1 into n plus c2 into n square up to c of n minus 1 n into n power of m minus 1 into r of n1. So in this, the n terms arises because simply r upon n alone isn't enough to provide linear independent solution for each multiplicity. So a special case arises when the characteristics equation yields repeated roots. If roots r have a multiplicity of m, the portion of the general solution considering to the roots is modified. Instead of simply ar upon n, it becomes c0 plus c1 into n plus c2 into n square up to cn minus 1 n into m minus 1 upon rn. So this modification ensures that we have enough linear independent solution to satisfy all these initial conditions. Here I have taken example 2 also, repeated roots in action. So in the first step, as we saw, first we'll do the recurrence. So a of n is equal to 4 of n, a of n minus 1 minus 4 of a n minus 2 with a0 is equal to 1 and a1 is equal to 3. Then what we'll do in second step, characteristic equation. So r square minus 4r plus 4 is equal to 0. Then at roots, we'll solve the roots. R minus 2 upon whole square is equal to 0. So the answer will be r is equal to 2, which is multiplicity of 2. Then at the fourth step, we'll see like an is equal to a plus bn into 2 power n. Applying initial conditions, a0 is equal to 1, where a is equal to 1, a1 is equal to 3, a plus b upon 2 is equal to 3. So by solving this kind of solutions, where we get 2b is equal to 1, where b is equal to 1 by 2. So by this we get to know that let's apply the concept of repeating roots with another example. Considering the recurrence relation, an is equal to 4an minus 1 minus 4an minus 2 with initial condition. So in this, resulting is an express formula for the sequence. So now we'll look into about the applications and further explorations. So where this kind of recurrence relation is used. So in the case of algorithm analysis, analyzing the time complexity of recurrence algorithm. For example, in DSA, as we see that in mud sort, tower of an eye, this kind of recurrence relation is observed. Then at graph theory also, counting paths or structures in specific types of graphs. Then we'll see in a financial modeling compound interest, loan payments, or population growth. Then we'll see in digital signal processing, analyzing the output of digital filters and systems. So these are applications which we use and further explorations. So thank you everyone for watching this video.